Last time, we practiced making formulas for ionic compounds using little paper puzzle pieces so that you actually had something to look at and manipulate, put together, see if things balanced out. What we're going to do today is try to go from using those puzzle pieces to being able to do formulas without them. So we're going to be using the periodic table, using our knowledge of what ions have what charges, and still trying to balance those out, but hopefully getting to where we can do this with just a pencil and paper. So we'll start with some definitions, since we really didn't do that last week when we talked about formulas for the first time. A chemical formula represents the type and number of atoms in the smallest representative unit of a compound. It's kind of a mouthful, but the reason that we have to say it that way is because there are different kinds of compounds that are made by different kinds of bonds, and they aren't all exactly the same. If we take water as an example, a water molecule has 2 hydrogens and 1 oxygen, and each water molecule is its own thing. Each water molecule is separate from the water molecule that's next to it. So even though when you have a bottle of water or a glass of water, it looks like it's one cohesive substance, and it is, each molecule inside that liquid or inside that substance is separate from the molecule that's next to it. Each molecule is its own thing. But when we talk about ionic compounds, which is what we're dealing with today, we don't have separate molecules. Instead, we have what we call formula units. A formula unit is the lowest whole number ratio of atoms in an ionic compound. It is not a discrete molecule. Ionic compounds are not separate molecules. If we were to look at a picture of an ionic compound, something like table salt, if you were to look at a picture of how the atoms are arranged, it would look a little more like this bottom picture here. Notice the difference between the top picture, 1 water molecule all by itself, and the bottom picture. There's way more than 1 sodium and 1 chlorine in that bottom picture. When we write the formula NaCl for sodium chloride, what we're saying is that for every sodium you have to have chlorine. But the number of those pairs that you can have is almost infinite. Ionic compounds are a lot like Legos. When you're building with Legos, you have to put them together in a certain arrangement or a certain ratio. Otherwise, the pieces won't click together, right? But if you have enough Legos, you can keep going. You can build as big of an object as you want. It's kind of how ionic compounds work. For every sodium, you have to have a chlorine. You can have as many sets of sodium and chlorine as you have atoms available. Salt crystals can be huge. You guys are probably familiar with salt blocks that you buy like at the hardware store, right? And you put them out if you're maybe for deer hunting or maybe for animals. Oh, about this big. Yes? No? That's entirely made of salt. It's just a giant salt crystal. So we have a ton of sodium and chlorines together. When we write the formula, we write sodium chloride. We write 1 set. You can have as many sets as you want. So there's a reason that we have to say a formula is the smallest representative unit of a compound. Sometimes that's a separate molecule, but sometimes it's not. Sometimes it's like Legos, and that's just the smallest ratio of stuff that you have to put together. Okay, so how do we write formulas? What are we actually doing today? You have to pay attention to what kind of compound you have. And there'll be 2 types, binary and ternary. Binary are the kind that have 2 types of atoms. So when you look at the formula or the name that you're trying to write a formula for, there'd be 2 things there, 2 elements there. next thing you have to pay attention to is what ions do those elements make? We're writing formulas for ionic compounds, so we have to make ions first. So we'll just take a real simple example, and we'll go through this step by step at first. Do the long way first, then the short way. That's usually how science and math work. And the first thing we need to do is figure out what ions each of these elements make. So if we started with just plain sodium, how many valence electrons does it have? One. Do you know how to figure that out by looking at the periodic table? Do you remember that from last semester? The first column has 1, the second column has 2. Skip the middle, skip the transition metals, then 3, 4, 5, and so on until you get to 8. So if we were going to draw the dot structure for sodium, we would put 1 electron next to it. And then we also talked about last semester, what ion would this make? Is it going to lose 1 or gain 7? Lose 1. So it loses its electron and becomes Na+. And there's a free electron now. Remember, it's a plus because it's lost that electron. There's a positive now that's not balanced anymore by that negative. Okay, so now we've got the sodium ion. Now we need to make chloride. So we start with chlorine, which has 7 valence electrons. And we have to figure out how that's going to make an ion. Is it going to lose 7 or gain 1? Gain 1. And where do you think that 1 is coming from? Conveniently enough, sodium already lost 1. So that electron that chlorine gains is the electron that sodium lost. And then for an ion, we end up with Cl-. And it's negative because it's picked up an extra electron. Now we have these 2 ions. We have Na+, we have Cl-. What do opposites do? Attract. And we have a +1 and a -1. So those 2 things attract, and they form a bond. When they form a bond, notice that the charges go away because they're balanced out now. When those 2 things come together and make a bond, those charges become balanced and the charges go away. And if we were just going to write the formula for this, of course it would just be NaCl. This is what's actually happening on the atomic level when you make an ionic bond. You have to have something lose electrons. You have to have something gain electrons. You end up with a positive and a negative. Those things attract and they make a bond. It's kind of a long process to write out though. Let's see if we can trim it down just a little bit. We'll do 2 more examples with the electrons and then we'll get rid of the electron pictures as well. Okay, magnesium sulfide. Going a little bit faster this time. How many valence electrons does magnesium have? Look where it is. It's 2. It's 1 column over. Is it going to lose 2 or gain 6? Lose 2. How about sulfur? How many does it start with? Look where it is. 1 more. 6. Is it going to lose 6 or gain 2? Gain 2. Where are those 2 coming from? Magnesium. So those 2 from the magnesium hop over to the sulfur. You end up with Mg plus 2 and S minus 2. Are those 2 things even? Do they balance? Yeah. So when you write the formula, you just get MgS. One more with the electron pictures. How many electrons does calcium start with? 2. Iodine? 7. How many does calcium want to lose? 2. How many does iodine want to gain? 1. Wait a minute. So 1 hops over to the iodine, but calcium still needs to get rid of an electron. So what do we need here? Think back to your rectangles. We need another iodine. And then calcium can lose its other electron. So then we have 1 calcium ion, 2 iodide ions. And what's the formula look like? CaI2. So hopefully by this point you feel pretty good about what the electrons are actually doing. You kind of have a grasp or understanding of what the electrons are actually doing. But you can see this process would get pretty long if you were going to draw these pictures all the time. So there's a faster way. And we call it Criss-Cross and Reduce. You start with a name. Aluminum oxide. Look up the charges, or the valences, for each of those elements. What charge would aluminum have when it makes an ion? You have to think a little bit. Think how many valence electrons it has. Does it lose or does it gain? It's going to lose. It's a metal. How many? 3. So it would be a +3. What is oxygen going to do? Gain 2, so it'll be a -2. Now when I start doing this, or when I teach students to start doing this, I have you write down the charges right above each of the names, just to give you a visual. And then we can actually start writing our formula. First step to this says crisscross. So you take the charge from each side and you swap it to the other side. So the 3 now goes with the oxygen, and the 2 goes with the aluminum. Notice that I dropped the positive and the negative signs when I did that. Because we talked about already, when you make a compound, when you make a bond, those charges are going to be balanced. The pluses and minuses are going to go away. So when you crisscross your charges, drop the pluses, drop the minuses, and just keep the numbers. And from here, we need to check and see if we can reduce. Will a 2 and a 3 reduce like a fraction reduces? No. So we're done. We just got to write the formula. And that looks like Al2O3. Let's try another one. Magnesium phosphide. What's the charge for magnesium? +2. How about phosphorus? -3. Once you know your charges, then you crisscross them. Remember to leave the plus and the minus behind. Do a 3 and a 2 reduce? No, so you write your formula. Mg3P2. Let's try another one. Aluminum nitride. Aluminum's charge is +3. Nitrogen is -3. Criss-cross, leave the signs behind. And what are these reduced to? 1 and 1. That's why you always have to check if you can reduce or not, because +3 and -3 balance with one of each. So the formula is not Al3N3, it's just ALN. It's the simplest whole number ratio, so you always got to check and see if you can reduce. One more of these. Lithium's charges? +1. Sulfur, we've already seen today. -2. Will these reduce? No. Li2S. Okay, now we're going to throw in a little twist. We're going to add some transition metals to these. Transition metals are no different except the charge for the transition metal is the Roman numeral in the middle of the name. So what Roman numeral is in the middle of this name? 1. So the charge on the copper is +1. Sulfur is still the same. You would look it up and find that it's -2. And from here, the process is no different. Crisscross your charges, check if they can reduce. You should end up with Cu2S. Remember, there were 2 exceptions to the transition metal rule, and they were lead and tin. Lead and tin are technically not transition metals, but they can have more than one possible charge as an ion. So they get a Roman numeral too. Also, what's this Roman numeral? 4. So this time lead is +4. Chloride, -1. Crisscross the charges, check if they reduce. They don't. So you have PbCl4. Okay, I said back when we started with the names, you had to pay attention to what kind of compound it is. The second kind of compound is called ternary. Ternary compounds are those that have more than 2 types of atoms or more than 2 types of elements. That means they have polyatomic ions in them. So for an example, lithium hydroxide. Lithium is a plain element whose name we recognize. Are you going to find hydroxide on the periodic table? No. So that means that's a polyatomic ion, and you have to look it up on your list. Where's your list? On the back of your notes packet. So look on the back of your notes packet, find hydroxide on the list. Look up what it is and what its charge is. So what's hydroxide? OH, and it's a -1. Lithium we know is a +1 based on where it is in the periodic table. Hydroxide we just looked up is a -1. Criss-cross and reduce. We need 1 of each. If we need 1 of each, do we need parentheses? No. So the formula is LiOH. see if you can do this one. Hydroxide is still the same, we just looked it up. Look for calcium's charge. How many hydroxides do we need this time? 2, which means we need parentheses. Because we need 2 hydroxides, not just 2 hydrogens. If we didn't have those parentheses, the formula would imply that we had 1 calcium, 1 oxygen, and 2 hydrogens. How about this one? What's aluminum's charge? +3. Find carbonate on the list. Carbonate is a -2. You should have found its formula on the back, which was CO3. Crisscross the charges. Do they reduce? No. Al2, CO3, and parentheses 3. We need the parentheses because we don't want this to say CO33. You have to have the parentheses to separate those. Try this one. Sodium is +1. What is sulfite? And its formula is? SO3. Be careful when you look up things on the chart that you pick the right one. Did you notice right next to sulfite there is sulfate, which is different? One letter changes what that is. So you have to be very careful that you look up the right thing on the chart. And then again, crisscross your charges, they don't reduce, so you write your formula as usual. One more. Ammonium sulfide. Which part of this are you looking up on the chart? Which of those 2 words is an element name that you recognize? Sulfur, sulfide. So this time you're going to look up the ammonium part on the chart. It is possible to have the polyatomic listed first. What's ammonium's charge? +1. Sulfur, of course, is -2. Crisscross and reduce and write your formula.